Section 2.2, Organizing Quantitative Data, the Popular Displays. We will look at these 7 objectives in this section. The first step in summarizing quantitative data is to determine whether the data are discrete or continuous. If the data are discrete and there are relatively few different values of the variable, the categories of data, which we'll call classes, will be the observations, just as we did with qualitative data. If the data are discrete but there are many different values of the variables, or if the data are continuous, the categories of data then, called the classes, must be created using intervals of numbers. So our first objective will be to organize discrete data in tables. In this example, we want to construct a frequency and relative frequency distribution from our discrete data. The data we have here represent the number of available cars in a household based on a random sample of 50 households. We want to construct our frequency and relative frequency distribution. So similar to the way we did with our qualitative data, we'll go through each data point and make a tally mark of what category it goes in. So notice the first one is the number 3, so we put a tally mark here. 4 will go here, 1 goes here, 3 will go here, and we'll continue so on. So now that we've gone through each data point, we want to count up how many tally marks in each category to give us our frequency. There were 4 households with 0. We had 13 households with 1 car, 22 households with 2 cars, we had 7 with 3, 3 that have 4 cars, and we had only 1 household that had 5 cars. Now we'll compute the relative frequency. Remember, we want to take the frequency divided by the total number of data points. So there were 50. So in each case, we'll take our frequency divided by 50. So in our first case, we have 0.08. And we'll round our data values to 2 decimal places in this case. For our second category, we have 0.26. Next, 0.44. Then 0.14, 0.06, and lastly 0.02. And these are our relative frequencies. Objective 2, we want to construct histograms of discrete data. A histogram is constructed by drawing rectangles for each class of data. The height of each rectangle is the frequency or the relative frequency of the class. The width of each rectangle is the same, and the rectangles touch each other. Here we want to draw a frequency and relative frequency histogram for the data we previously looked at, our number of cars per household. So here's the frequency and relative frequency distribution we came up with earlier. Now let's draw our histogram. This is the frequency histogram, and notice that the heights of the bars represent the number of cars in that category. The bars are the same width, and the bars touch one another. Here we have a very similar picture, but this one is the relative frequency. And notice we've changed the numbering on our vertical side here with the relative frequency. Instead of going up to 50, now we're doing up to 0.5 and going by 0.1 decimal place each time. Still notice that the heights of the bars are representing the relative frequency of that category, and it follows the same rules for our histogram. Objective 3, we want to organize continuous data in tables. Classes are categories into which data are grouped. When a data set consists of a large number of different discrete data values, or when a data set consists of continuous data, we must create classes by using intervals of numbers. So let's look at how to do that. The following data represent the number of persons aged 25 to 64 who are currently work disabled. And here we have that data. The lower class limit of a class is the smallest value within the class, while the upper class limit of a class is the largest value within the class. The lower class limit of our first class is 25. The lower class limit of the second class is 35. The upper class limit of the first class is 34. The class width is the difference between consecutive lower class limits, so our 25 and 35. That gives us that the class width of the data given above is 35 minus 25, which is 10. Now let's look at an example. We want to organize continuous data into a frequency and relative frequency distribution. The following data represent the time between eruptions in seconds for a random sample of 45 eruptions at the Old Faithful Geyser in Wyoming. We want to construct our frequency and relative frequency distribution of the data. The smallest data value in our table was 672, and the largest data value was 738. We'll create the classes so that the lower class limit of the first class is 670, and the class width is 10, and we obtain the following classes. Using those classes as our categories, let's tally our data values into our distribution. The first value of 728 will fit into this category here. We move on now, we have 730, which fits into the next class below it. 726 will also fit into this class here, and we continue so on. Now that we have tallied each data value, we will count up our tally marks to give us our frequency. So our first class we had 2, then 0, then we had 7, 9, 9, 11, and 7. To construct our relative frequency, remember we take the frequency and divide it by the total, which was 45. So each value will be divided by 45. So our first frequency, we have 0.044. And then we have 0. Next is 0.1556. Then we have 0.2 and 0.2. Next we have 0.2444. And the last one would be 0.1556 again. So here we have our frequency and our relative frequency distribution for our continuous data. The choices of the lower class limit of the first class and the class width were rather arbitrary. There is not one correct frequency distribution for a particular set of data. However, some frequency distributions can better illustrate patterns within the data than others, so constructing frequency distributions is somewhat of an art form. Use the distribution that seems to provide the best overall summary of the data. In this frequency distribution, the class width is 5. Notice that we had a great deal more classes with a class width of 5. If we have too few classes, this will cause a bunching effect, and then too many will spread the data out so that you're not able to reveal any kind of pattern. So although there's no right frequency distribution, there are bad ones. So we use the following guidelines for determining the lower class limit of the first class and the class width. In order to choose the lower class limit of the first class, we first choose the smallest observation in the data set, or a convenient number slightly lower than the smallest observation in our data set, which is what we did previously. To determine the class width, we decide on the number of classes. Generally, there should be between 5 and 20 classes. The smaller the data set, the fewer classes you should have. Then we determine the class width by computing the following. The class width will equal the largest data value minus the smallest data value divided by the total number of classes. Objective 4, we want to construct histograms of continuous data. So looking at the data from our earlier example, we see our frequency and relative frequency distribution listed, and we're going to look at the histogram for our class width of 10. Notice that the heights of the bars represent our frequency and the widths are the same, and the numbers we used were the lower class limits. And here we have our relative frequency distribution. Here's the frequency distribution when the class width was 5. Notice that the data is much more spread apart. Objective 5, we want to draw stem and leaf plots. A stem and leaf plot uses digits to the left of the rightmost digit, or the last digit, to form the stem. Each rightmost digit, our last digit, forms a leaf. For example, a data value of 147 would have 14 as the stem and 7 as the leaf. We would split it at that last digit. So let's look at an example. An individual is considered to be unemployed if they do not have a job, but are actively seeking employment. The following data represent the unemployment rate in each of the 50 United States, plus the District of Columbia in June of 2008. And here's that data. We let the stem represent the integer portion of the number, and the leaf will be the decimal portion. For example, the stem of Alabama, which was 4.7, will be 4, and the leaf will be 7. Notice that we will not include the decimal anywhere in the stem and leaf plot. We'll only be using the numerical values. So looking at our data, we want to construct our stem and leaf plot. And the way we do that is we list all of the stems. So we're dividing them at the decimal. And our lowest value was 2. And we have all the way up to 8. And we go data point by data point. So we look at Alabama first, and it was a 4 for the first digit and a 7 for the last. So that is our first leaf. Then we look at Alaska. We have 6.8. So we have a 6 and then we have an 8. And so on. So here we've tallied all the data into our stem and leaf plot. We've listed all of the leaves with the appropriate stem. The next step is to put the leaves in order from lowest to highest. And here is our final stem and leaf plot once we've put our leaves in order from lowest to highest. So here are the rules for constructing our stem and leaf plot. Step 1, the stem of a data value will consist of the digits to the left of the rightmost digit. The leaf of a data value will be the rightmost digit, or the last digit. Step 2, we want to write the stems in a vertical column in increasing order. Draw a vertical line to the right of the stems. Step 3, we write each leaf corresponding to the stems to the right of the vertical line. And step 4, within each stem we rearrange the leaves in ascending order, or from the lowest number to the highest. We then title our plot and include a legend to indicate what the values represent. For instance, in our last example, we would need to know that there was a decimal value between the stem and the leaf for each point. When data appear rather bunched, we can use split stems. The stem and leaf plot shown on the next slide reveals the distribution of our data better. As with the determination of class intervals in the creation of frequency histograms, judgment plays a major role. There's no such thing as the correct stem and leaf plot. However, some plots are better than others. Here's an example of a split stem and leaf plot using the data from before. In each case, when we split the stems, our first stem represents the data values from 0 to 0.4. So this one is 3.0 to 3.4. And this next stem represents the data from 3.5 up to 3.9. One advantage of stem and leaf diagrams over histograms is that once a frequency distribution or histogram of continuous data is created, the raw data is lost, unless it's reported with our distribution. However, the raw data can always be retrieved from the stem and leaf plot. Objective 6 is to draw dot plots. A dot plot is drawn by placing each observation horizontally in increasing order and placing a dot above the observation each time it is observed. In this example, we will draw a dot plot. The following data represents our number of cars in our household based on our random sample of 50 households. So notice that the different categories of cars was 0 through 5, and those are listed at the bottom. Above each one we have dots. These represent how many times that data value appeared. So each time it appeared we put a dot. If you notice in the first case, there were 4 zeros in our data set, and there are. And it follows the same pattern throughout. Objective 7, we want to identify the shape of a distribution. In a uniform distribution, which we see in our first picture, the frequency of each value of the variable is evenly spread out across the values of the variable. A bell-shaped distribution, that's our next picture, picture B. The highest frequency occurs in the middle, and frequencies tail off to the left and right of the middle. Skewed right is our picture C. The tail to the right of the peak is longer than the tail to the left of the peak. Also, if you were to draw an arrow using the tops of the bars, you would notice that the arrow is pointing to the right. Skewed left, which is our last picture, the tail to the left of the peak is longer than the tail to the right of the peak. Or if you drew an arrow, it would be pointing to the left. So in this example, we want to identify the shape of our histogram, which represents the time between our eruptions at Old Faithful. The peak occurs here, and notice that the tail to the left of the peak is longer than the tail to the right. So this picture is skewed left.